Last section of chapter 12 on surface area and volume, we're going to talk about the volume of spheres. If you remember, when we talked about the surface area of a sphere, it didn't have any lateral area. It came out to be 4 pi r squared. The only measurement we have is the radius, so we have to relate that with pi r squared. And then it comes out that relationship is 4. So remember that area units are always squared. And as we go about deriving our formula for volume, I'm actually today just going to give you the formula for volume, but there is a really cool derivation that I will link in Schoology. For volume, we need the units to be cubed. And so as we start to think about what types of numbers and relationships that we're going to see in our volume formula, we should expect to see something that involves the radius being cubed. So as a reminder, let's look at our visual. A sphere is a round ball that is made up with a radius from the center to any point that we choose on the sphere. And so here's what our volume relationship for a sphere is. Here is our formula. The volume of a sphere is going to be equal to 4/3, 4/3, pi r cubed. 4/3 pi r cubed. And some of you might be sitting at home listening to this saying, oh, yes, I remember something about that. For some reason, throughout time as we learn these formulas, this is one that I think sticks pretty well in people's minds, probably because it's got this kind of funny fraction, and then it's 4/3 pi r cubed. So that is the volume of our sphere. So what we're going to do is the formula is pretty straightforward. We're going to do one example of that, and then we're going to work through a couple of examples of using relationships of spheres. So for number 1, it says a sphere has a radius of 8. Find the volume and the surface area of this sphere. So let's start with the volume. So when it comes to this formula for a sphere, it has a radius of 8. The only thing that we need to do is substitute the 8 in for that spot for r cubed. And so this would make our volume 4/3, 4/3 pi times 8 cubed. And 8 raised to the 3rd power is 512. So what that gives us, to kind of give you some help with fractions here, gives us 4/3 of 4/3, and then we'll say times 512 pi. Whenever I leave things in pi form, I think of the pi always usually goes at the end once we multiply out our numbers. Usually it'll be in the middle of the formula, and then at the end of the problem, we move it to the back of the numbers. So now with our fractions, it's the 4 and the 512 that get multiplied together. And then if that number divides by 3, then we'll do it. If not, we'll leave it in fraction form. So let's try this. So that gives us 4 times 512, which is 2048. Let's try dividing it by 3. Okay, so we get a fraction, or we get a decimal, so let's leave that. And so that gives us that the volume is 248. And then since the pi is a number that is a whole number, it goes with the top of the fraction. So 248 pi over 3. And that is our volume in exact form left as a reduced fraction. I know many of you like decimals. I know you like multiplying the pi in. As you get into more complex math, we want to leave things in this exact form, even if it's slightly uncomfortable. So this is our volume. And so for our surface area, it is 4 pi times r squared, which is 8 squared. That gives us 4 times 64 pi. And my apologies if you hear sirens in the background. And 4 times 64 gives us 256. So we get 256 pi. And we should write some units. This is units squared for surface area. And then for volume, it is units cubed. So hopefully this shows you how to use this formula. All right, so next up with number 2, it says a cone is inserted in a hemisphere with a diameter of 12. So let's go ahead and draw that. And a hemisphere is half of a sphere. So we've got a diameter of 12, which means cut it in half. Our radius is 6. Find the volume between the two solids. So as you've started to work this through, hopefully you have realized that when we are looking for leftover area, leftover volume, we can take the two parts and subtract their volumes from each other. So if I find the volume of the hemisphere, that will be all the space where the cone currently is. If I want to remove the space of the cone, I need to find that volume and I will subtract it. So the volume between the two of them will be the volume of the hemisphere minus the volume of the cone. So then this is a great time to review these formulas. So for the volume of a hemisphere, it's going to be half of 4/3 pi r cubed because it's half of a sphere. So it's 4/3 pi times 6 cubed. Now, we could make our lives a little bit easier. If I took the two fractions 1/2 and 4/3, that's going to make this 2/3 pi times 6 cubed. Let's go ahead and actually do that. 6 to the third power is 216. So 2/3 times 216 pi. If this is not how you work, find the volume of the sphere and then just make sure to divide it by 2. But I like this method, so now let's try 216 times 2 divide by 3. And nice, look at that, we get a whole number, 144 pi. So that's our hemisphere, 144 pi. Let's go ahead on to our cone. So for the cone, remember that the volume of a cone is 1/3 pi r squared times our height of h, or 1/3 pi r squared h. Now here's the challenge, they did not tell us the height. Here's where we want to go back to our knowledge. So the kind of pink salmon line I just drew in is our height. This is a hemisphere. So what that means is from that center point, every line I draw to the edge is going to have the same length as our radius. So that means this cone, or this height, is also going to be 6, which is awesome. So that makes this 1/3. Then I'm going to go ahead and just do the pi r squared. That's 36 pi times a height of 6. Here, thinking about some numbers, so we can do this in our head. 1/3 of 36 is 12, and 12 times 6 is 72. So that gives us a volume of 72 pi. If you don't trust your math, you could do 36 times 6 divided by 3. But trust your mental math, trust that you can do it. So then let's go back. The volume of our shaded area, and notice so far, I have not multiplied the pi in at all. Please follow my example that we're going to leave pi in our answer so that we can see these numbers that make up our value, unless I tell you to round it, and this problem does not say to round it. So that makes this volume come out to be 144 pi minus 72 pi, which I think should also give us 72 pi. Let's see here. Oops, minus. Yeah, so interesting. This is fascinating. So that gives us 70 pi cubic units. And that's really fascinating to think about, that the empty space left around would be equivalent to the volume of the cone itself when it's inside a sphere. Interesting. All right, so here's the next one. Even if you feel like you got it, I would stick with me through at least problem 3, because we're going to go back and we're going to actually do some factoring. We're going to work more with the variables than we have ever worked with them before. So for number 3, here's what we got. The surface area of a sphere is equal to its volume. What is the radius, and it has to be greater than 0, of the sphere. So I have a sphere. Best way to draw them is draw a circle, and then you can kind of draw around it to make it look like a sphere. We don't know what the radius is, and that's our variable that we're looking for. Remember that surface area is equal to 4 pi r squared, and volume is equal to 4/3 pi r cubed. So it says that those are equal. We don't know what value they are, but I have two formulas that both involve the radius. Whenever we have quantities that are equal and they use the same variables, well, we have the power to set those equal to each other. So that means that if the surface area is equal to the volume, that means 4 pi r squared equals 4 thirds pi r cubed. So now what we're going to do is we're going to do some algebra and solve through. Let's first clear out the fraction just to make our lives a little bit easier. Multiply by 3, and that makes this times 3, 12 pi r squared equals, the 3's cancel, so that equals 4 pi r cubed. Here's what we're going to do. We have a variable that we need to factor out. I know that a lot of you might be thinking, well, I could divide by r squared and I could cancel some r's. When you have a variable, you don't want to divide out the variable. Any numerical value like a number or pi, anything that's a number, you can do that. But with an unknown, we don't want to do that. So instead, we're going to use factoring. So I'm going to subtract 12 pi r squared to the other side. And if you want, we can cancel out the pi's. So let's do that. Let's cancel out the pi's. And this leaves us with 0 is equal to 4r cubed minus 12r squared. So now, rather than dividing, whatever you would have divided, we are going to use a common factor, greatest common factor, and factor that to the front. So what do they have in common? Both of those terms, the 4 pi r cubed and minus 12r squared, have a multiple of 4 in common and a multiple of r squared in common. So when we factor that, we write it in the front, and then we multiply by whatever is left over. The 4r cubed, I've factored out the 4, I factored out 2 of the r's, so that leaves me with r minus, and then we've pulled out both of the r's from r squared, and then we factored out the factor of 4, so that leaves us with minus 3. And so now that we've factored, what factoring tells us is we can take both pieces and set them equal to 0. 4r squared equals 0, or r minus 3 equals 0. The first one comes out to be a radius of 0, so we don't want that. Radius of 0 doesn't do anything for us. But the second one, when I add the 3 over, gives us a radius of 3. All right, so then that helps us work this out here. If you would like to see another one, I'm going to kind of quickly work through the next one. And if you think that you have, if you think you've been having difficulties with this, then we can work through another one here. So number 4 says the total surface area of a hemisphere is equal to its volume. So for the total surface area of a hemisphere, remember we have a circle with a sphere underneath like this. And so I need to do 2 things. So one, for the surface area, the curved bowl part on the bottom is going to be half of that 4 pi r squared. So it would be 2 pi r squared. But then we also have the lid, the top, that is also considered now a surface area when we cut it off with a hemisphere. And that's a circle, so that would be plus pi r squared. So that means the surface area of our hemisphere is 3 pi r squared. Next up, for the volume, remember before when we divided it in half, it made it 2/3 pi r cubed? Well, half of 4 is 2, and so that would make sense to us that for a hemisphere, the volume should be 2/3 pi r cubed. And you can use that relationship if that's helpful to you. So now, just like we did before, if they're equal, we're going to set up those equations and we're going to set them equal. So that means 3 pi r squared is equal to 2/3 pi r cubed. All right, not necessary, but I think super helpful. We can multiply by 3, so that makes this 9 pi r squared equals 2 pi r cubed. We can divide by pi and cancel them, so the pi's are gone. And so then now we have 9r squared equals 2r cubed. And next up, we took these values and we subtracted. I would subtract the number that has the lower power of r, so that 9r squared, over to the other side. So that makes this 0 is equal to 2r cubed minus 9r squared. Now this time, 2 and 9 have no common factors, no common multiples. And so I can only factor out the r squared that is in common. So that makes this 0 equals r squared times what's left over, 2r minus 9. That term out front, we can set it equal to 0. It's still going to give us a radius of 0. But we get 2r minus 9 equals 0. That means 2r equals 9. Or we have a radius of 9 over 2, or 4.5. So if the total surface area of a hemisphere equals its volume, the only time that happens is if the radius is 4.5. And that's kind of cool to see that relationship here. All right. For number 5, this is generally in class the challenge that I would give for you to work on with your group. So this is a nice problem that takes this forward and helps us to figure out some dimensions. In the key, I will work this all the way through. And so I would encourage you to work this through. And then if for some reason there's a lot of us that are getting stuck, let me know and I will make a screencast of this problem. But for now, I want to leave it. I want you to try it. And then I want you to use the key, use the numbers. And if you have trouble, use those numbers to try to work through this. Okay, that is it. Next up is the 12.6 practice. And then when you finish that 12.6, your whole packet is done. Go ahead and submit that to Schoology and you are done with the content. And then we'll get into the review and the assessment for the unit from there.